Hemoglobin dissociation curve, part of Desjardins' Cardiopulmonary Anatomy and Physiology, Chapter 6. So we talked about in the previous lecture how oxygen is carried on the hemoglobin. Now we're going to talk about the oxyhemoglobin dissociation curve. So the oxyhemoglobin dissociation curve is also known as the hemoglobin-oxygen equilibrium curve. It's part of a nomogram that graphically illustrates the percentage of hemoglobin chemically bound to oxygen at each oxygen pressure, or PO2. It also shows the content of oxygen. So if you look to your right, you'll see the percentage of hemoglobin saturation. This can be reflected as the SaO2. You also see at the bottom of this curve a PO2 in millimeters of mercury, or torr. And then on the far right-hand side, you see the oxygen content in milliliters per 100 mils of blood, or volumes percent. Now we've talked about content equations as well as SaO2 and PO2. You can see in yellow the normal PO2 part of the curve from 80 to 100 torr. There's a flat part of the curve at the top, and you can see that is about at 90%. After 90%, and if you use this as a graph and go over from 90% and down, you'll see that at 90%, the PO2 at the bottom is 60 for a normal oxyhemoglobin dissociation curve, which is what we're looking at here in the graphic. Figure 6.3. Let's talk about that flat portion of the curve and its clinical significance. Increasing the PO2 beyond 100 torr adds very little oxygen to the blood plasma. Remember that dissolved O2 is PO2 times 0.003 is equal to the dissolved oxygen in the blood. However, let's talk about that steep portion of the curve that you saw, that part that's below the 90% level and the 60 PO2 level. Reduction of PO2 below 60 torr causes a rapid decrease in the amount of oxygen bound to hemoglobin. However, diffusion of oxygen from the hemoglobin to the tissues is enhanced at these low PO2 states. Hey everybody, so I want to talk about the P50. This is a really important point of reference on the oxyhemoglobin dissociation curve. Remember that P50 is just a point of reference. It's a marker on the oxyhemoglobin dissociation curve, and what it represents is the partial pressure at which hemoglobin is 50% saturated with oxygen. Normally, this is a PO2 of 27 torr on a normal oxydisassociation curve. But what the P50 can tell us and why we use it as a reference point is whether the curve is shifted left or right. Let's talk about that. When the curve shifts to the right, the P50 increases or is greater than 27 torr. So on the bottom, that PO2 will be greater than 27 torr when the curve shifts to the right. Now, if that's the case, when the curve shifts to the left, the B50 diminishes below 27. So anything 26 or below, a PO2 of 26 or below, means the curve has shifted to the left. A PO2 of 28 or above means the curve has shifted to the right. Again, P50 is simply a reference point for us to know whether the curve has shifted to the left or the right. Well, why is that important? Let's talk about that. The P50 represents, and you can see it here, represents the partial pressure at which the hemoglobin is 50% saturated with oxygen. This is a visual representation of what we just talked about. You can see here in blue that when the oxyhemoglobin dissociation curve shifts to the right, the P50 increases. With this right shift, the PO2 is 40 at 50% saturation. If you look to the red colored area, when the oxydisassociation curve shifts to the left, the P50 decreases. When looking at this visual, you can see that the P50 for a left shift on the current curve is at 10 PO2 at the bottom. When looking at the red line, which is a dead-on normal curve, when you go across and use the graphical representation, trace it across and then down, the PO2 is at exactly 27. Factors that shift the oxygen dissociation curve. They can shift it either to the left or the right. Changes in pH, changes in temperature, carbon dioxide, 2,3-biphosphoglycerate, or BPG. And back in the day, it was called 2,3-diphosphoglycerate, or DPG, and you'll see it both ways in reading materials. Fetal hemoglobin, the presence of it. Carbon monoxide hemoglobin. So factors that shift the curve to the left and the right are pictured in figure 6.6 in your book. I want you to look at this graphic, and things that shift the pH being increased, the PCO2 being down, the temperature being down, BPG being down, fetal hemoglobin, and carboxyhemoglobin, all of those things will shift the curve to the left. Newborn babies that have fetal hemoglobin on board generally have a left-shifted oxydisassociation curve, and they will hang on to oxygen quite tightly. Things that shift the dissociation curve to the right: a diminished pH or acidotic pH, an increased CO2, increased temperature, and increased DPG. This allows the hemoglobin to release oxygen quite easily. Left-shifted oxydisassociation curve means hemoglobin hangs on tightly to oxygen. A right-shifted oxydisassociation curve means that oxygen hops off easily from the hemoglobin. So let's talk about the clinical significance of shifts in the oxyhemoglobin dissociation curve, or what are you going to see at the bedside? When an individual's blood PaO2 is within normal limits, 80 to 100 torr, shift to the oxydisassociation curve to the right or left doesn't significantly affect the hemoglobin's ability to transport oxygen to the peripheral tissues, those things like heart and lungs and brain. This is because shifts at this pressure range, 80 to 100, occur on that flat portion of the curve. However, when an individual's blood PaO2 falls below the normal range, a shift to the left or to the right can have a remarkable effect on hemoglobin's ability to pick up and release oxygen, due to the fact that shifts below the normal range occur on that steep portion of the curve. So, if your patient has a SaO2 below 90% or a PO2 below 60, this will apply. We're going to talk about an example. So consider loading and unloading oxygen during the following clinical conditions. Imagine loading oxygen onto hemoglobin as blood passes through the alveolar capillary system at a time when the alveolar oxygen tension, the PaO2, is moderately low, around 60 torr. Normally, when PaO2 is 60 torr, plasma O2 is about 60 torr, and hemoglobin is approximately 90% saturated, pictured here. As you can see, PO2, P big AO2, 60 in the alveolus, oxygen's diffusing, and P little AO2 is about 60 torr, not much different. Hemoglobin is 90% saturated with oxygen. This is shown in your book in figure 6-7. If, however, the oxygen dissociation curve shifts to the right, the hemoglobin will be about 75% saturated with oxygen as it leaves the alveoli. Here's a right shift that we're talked about, pictured here. When the P big AO2 or alveolar oxygen tension is 60 torr at a time when the curve has shifted to the right due to a low pH. The hemoglobin is 75% saturated with oxygen due to the right shift. In view of the drop in oxygen saturation during a right shift with low oxygen levels, it should be stressed that total oxygen delivery may be much lower than indicated by the PO2 value when a disease process is present that causes the oxydisassociation curve to shift to the right. Although total oxygen delivery may be diminished in the previous situation, blood plasma at the tissue sites does not have to fall as much to unload oxygen from hemoglobin. In other words, oxygen oxygen hops off of hemoglobin easily. Normally, when the plasma PO2 is 60 torr, the PO2 must fall about 35 torr just to free 5% of oxygen for tissue metabolism. However, if the curve shifts to the right, again in response to an acidotic pH, plasma PO2 at the tissues would only have to fall from 60 torr to about 40 torr to unload that 5% of oxygen from the hemoglobin due to the right shift. When plasma PO2 is 60 torr at a time when the curve is shifted to the right due to an acidotic pH, PO2 must fall approximately to 40 torr, pictured here, to free that 5% of oxygen for metabolism. Now let's talk about what happens when the curve shifts to the left. Left shifts happen when the pH is alkalotic. If the oxygen dissociation curve shifts to the left when the alveolar O2 is 60 torr, at a time when the curve has shifted to the left because of a pH of 7.6 or an alkalotic pH, hemoglobin will be 95% saturated with oxygen instead of that 90% that it normally would be. When the alveolar oxygen is 60 torr at a time when the curve has shifted to the left due to alkalosis, this is pictured in figure 611 in your book and here on the screen. You can see that at a normal time, the SaO2 would be 90%. However, with a left shift at a PO2 of 60, the oxygen saturation of the blood is now 95. Although total oxygen increases in the previously mentioned situation, blood plasma PO2 at the tissue sites must decrease more than normal for oxygen to dissociate from the hemoglobin. It's harder for that oxygen to get off of the hemoglobin. It takes more. For example, if tissue cells require 5% of oxygen at a time when the oxyhemoglobin dissociation curve is normal, plasma PO2 will fall from 60 torr to about 35 millimeters of mercury to free that 5% of oxygen from the hemoglobin. But if that curve shifts to the left because of an alkalosis, an alkalotic state, plasma PO2 at the tissue sites would have to fall from 60 torr to about 30 torr to unload that same 5% of oxygen from the hemoglobin for the tissues to eat and metabolize and do all the stuff they need to do. When the plasma PO2 is 60 at a time when the curve is left shifted due to alkalosis, the PO2 must fall to approximately 30 torr to free that same 5% of oxygen, and that's pictured here. with various manipulations of the content of oxygen, the content of mixed venous oxygen, and the capillary content. All of those values can serve as excellent indicators of an individual's cardiac and ventilatory status. Clinically, some of the most common oxygen transport studies performed are total oxygen delivery, or total oxygen content, arterial venous oxygen content difference, so the difference between the content in the arterial blood and the content in the venous blood, oxygen consumption, how much are those tissues using, oxygen extraction, how much did those tissues actually take, and mixed venous oxygen saturation, as well as pulmonary shunt calculations. Here's a summary of important normal values. Total oxygen delivery, or DO2, is about 1,000 milliliters per minute. A normal arterial venous oxygen content difference, or CA minus V O2, is 5 vols per cent. Oxygen consumption, or VO2, is equal to about 250 mils of oxygen per minute. And an oxygen extraction ratio that's normal, or O2ER, is about 0.25 or 25%. This is the end of our lecture for today about the oxydisassociation curve. Thanks for watching, everyone. Have a great day.